This. So I'm going to start here on our chapter 5 on gas laws. Okay, so maybe some of you might have some familiarity with this from some previous chemistry courses, but if not, that's okay. We're starting from the beginning. Okay, so we start by noting that the definition of pressure, not what you're experiencing now, being a college student in the year 2020 with a pandemic and forest fires, right? Pressure, as related to gases, is by definition force over area. So a force acting over an area, okay? And the proper, what I'll call, our SI unit, our standard, or the system international unit, is the Pascal. So that's a named unit that's named after a person, Pascal. And by definition, a Pascal is 1 Newton per square meter. So a Newton is a unit of force, and a square meter is a unit of an area. So that gives us a Pascal. Something you might be more familiar with is the pound per square inch, the PSI, right? So that is 1 pound of force per square inch, okay? And it's important to note here, so atmospheric pressure, what we experience at sea level, so right, 1 atm, so we'll say at sea level, okay, assuming there's no weather systems changing the pressure, that's the same thing as 14.7 pounds acting over a 1 square inch area, okay? In terms of pascals, that's also the same as this crazy number, 1.01325 times 10 to the 5th pascals, or that's the same as 101 kilopascals. So I take this number and divide it by 1,000, right? I can still do all of my scientific notation stuff. So about 100 kilopascals is 1 atmosphere. Okay, so what about all these other units? Well, there's a really famous device here. This is called a barometer, a barometer, okay? And this was actually invented by a gentleman of the name Torricelli, an Italian scientist who was Galileo's graduate student. Pretty cool stuff. So we have this thing called the barometer, invented by Torricelli. And the idea of this device is you have this pool containing liquid mercury, and atmospheric pressure is pushing on that liquid pool just like it's always pushing on everything all the time. And you have this inverted tube. So if I draw like a cross section of this, right, here's that liquid, and the tube is all the way down in the bottom of that liquid, okay? And as the atmosphere pushes on this liquid, you notice here that it's evacuated, so there's vacuum between the top of the tube and the rest of the liquid. And so what that, in turn, the atmosphere pushing on this liquid forces the liquid to rise up that column, okay? And as it turns out, at sea level, at exactly 1 atmosphere, the height of this column will always be the same. Of course, that's at exactly atmospheric pressure. And as it turns out, the height of that column of mercury is 766 millimeters. Now, it's important to note, if that were a different liquid, if it were water, for example, it would be much taller. If this were water, it would actually be closer to like 13 meters, like a full 1-story house. And that's due to the difference in the density of water versus mercury. So mercury is very dense, so that's why this only goes up 760 millimeters. So we call that measurement, 1 atmosphere, 766 millimeters of mercury, we call that 766 torr, for Torricelli himself. And if you're kind of a weather buff, if you're into looking at like pressure and what's going on and with atmospheric conditions, you will also know that that number, 766 millimeters of mercury, is the same as 29.92 inches. So that's just converting an inch to a meter, or excuse me, converting a millimeter to an inch rather, okay? So all of these units, I'm not going to make you memorize, you'll be given them, but you do need to be able to interconvert pressure units back and forth, okay? So for example, suppose on one day we find that it's 0.956 ATM, right? Let's say there's a low pressure system out there, there's a storm, and we see that it's 0.956 atmospheres. How many torr would that be? Well, look, we can do the same thing where I apply my dimensional analysis skills, and I know from this chart, 1 atmosphere is 766 torr. Okay, so on a day, you know, where there's slightly less atmospheric pressure, oops, I got a calculator right here. So I can say 0.956 times 760. And on that particular day, it would be, you know, with 3 sig figs, let's say, 727 torr, for example, okay? So be able to use any of these types of conversions in the same way that we've been doing, okay? You don't have to memorize these units, but you should have some amount of familiarity with them, okay? So let's move on. So what exactly... oh my God, you know what I just noticed? I've been skipping my whole first slide this whole time. That's okay, I'm not re-recording it. All right, so all this stuff applies. This barometer, Torricelli. What I wanted to tell you first, I realized something about that was off. What exactly is atmospheric pressure in terms of something that we're familiar with? Well, as it turns out, our atmosphere is really, really thin in comparison to the size of our planet. Right, it's only about 50 kilometers thin, but our planet's circumference is about 40,000 kilometers. So the atmosphere is really, really thin. And if there's a ginormous area, right, 5 times 10 to the 14 meters squared. Well, as it turns out, the mass of our entire atmosphere, even though it's really thin, it's quite massive, 10 to the 18 kilograms. And what's keeping that pressure down is gravity. Right? This is a massive amount of force, right? Force due to gravity being exerted on us all of the time. Gilbert, the author of our book, did a really cool calculation and said the equivalent force of this, the equivalent force of the atmosphere is if you took your hand out like this picture is showing, and I've lost track of how many books there are here, but this is accurate. This is accurate for the force due to the atmosphere. This number of books balanced on your single hand, right? The square area, the surface area of my hand, and the mass of all of those books. So to me, what's always impressive about this kind of scale is it shows us that our bodies are quite strong, right? We have this atmospheric pressure being exerted on us all the time. We evolved this way, okay? That's why as humans, we're actually quite sensitive to very small changes in weather or atmospheric pressure. You might have a family member that has an injury who can tell when a storm is coming, right? Because there might be a change in atmospheric pressure and they feel it in their joints. That's not an old wives' tale. That's for real. We've come accustomed to being quite sensitive to changes in atmospheric pressure. So this was the first slide I was supposed to do. Then I was going to tell you about all these numbers and units. C'est la vie. We did them both. Okay. So let's move on. So now I want to talk about another type of device, very similar to a barometer, but it's just slightly different in its construction, a manometer. Okay. And so there's 2 ways that we can use a manometer to measure pressure. One in which we have greater than atmospheric pressure. Okay, so in this case, you know, perhaps you have a sample, and I'll say the pressure of the sample is greater than the pressure of the atmosphere. So then in that case, this tube, right in the barometer that was closed, then it was evacuated. So this tube would be open. okay? And the atmosphere pushes on this liquid level. And when this is all closed, and this is what makes this a manometer, by the way, because it's not measuring atmospheric pressure, it's measuring the pressure of the sample. Barometers measure atmospheric pressure. Manometers measure pressure of a gas sample, okay? And so now what happens is as soon as you open the sample, you've got the sample pushing on the liquid level, but the atmosphere is also pushing on the liquid level. And of course, if the pressure of the sample is greater than the pressure of the atmosphere, it will displace the liquid in this U-tube. And this delta H, that difference in height, will give you what the actual pressure is. Because once again, we know that the pressure of the atmosphere is supposed to be 766 millimeters of mercury. Okay, we measure whatever that is, and then the difference gives us the pressure of the sample. Okay, great. So now what if we have less than atmospheric pressure? Well, we can still use this manometer, but now this end is closed. Okay, and so now there's no force opposing this thing, like in the atmosphere. Okay, and so let's just let me write this down really quick. P sample is less than P ATM. And so now when you open this up, okay, what ends up happening is there was actually some slight amount of pressure in there, as well as in there. But now when this opens, okay, all of that pressure gets sucked in to the sample. And as you can see, that reduces the height of that. And then the height, the change in this height only gives you the pressure of the sample in that case. Okay? So moving on. So now, as a reminder, when we do stuff with gases, we are going to primarily use the Kelvin scale. We will occasionally have some, some problems that have centigrade, that have Celsius in them, but we will predominantly use the Kelvin scale. So this is just a reminder. I do want you to commit to memory the conversion of Celsius to Kelvin or Kelvin to Celsius. So remember this equation. I'm just kind of backing up and going to our pressure units. You don't have to memorize any of these, okay? These will be given to you, okay? So